Hi everyone, can you hear me out back there? Great. Well, this morning I woke up very early when it was still dark and went outside to let my dog out, and I looked up and there were a lot of stars. I live about 30 minutes west of here, but I encourage you all, it looks like another great night to go out and look at the stars, and you can wonder what kind of planet is around those stars, because it appears that nearly all stars have planetary systems. Although, just a little caveat, most of those stars you can see, they're giant stars, and our techniques can't easily search for planets around giant stars yet. Well, people have been wondering about what's out there, what is out there among those stars for thousands of years, since the time of the Greek philosophers. But what's really curious is even hundreds of years ago, in the late 1700s, our founding fathers of the United States of America, they wrote down that suns are stars with planetary systems. Not sure where they got that from. I read this book once. It was like a diary of a girl from the Midwest in the 1850s, and she learned in school that stars are suns and there's humans there. And that was because Bessel, this German mathematician and astronomer, figured out how to measure parallaxes precisely and distances to stars. Somehow that percolated down to school. In 1920s or 30s, astronomers and optical physicists first started realizing they might be able to search for signs of life on planets in our own solar system. And the British astronomer, James Jeans, he even said that oxygen that we have here on Earth, created by life, could be a sign of life elsewhere. So I invite you to think about, during my lecture, what will we get bullet pointed for here? In future textbooks, 100 years from now or so, are we going to be able to do anything in the search for life elsewhere? So you can think about that during my talk, and let us see where this takes us. So what I'm going to talk to you about today is an introduction on biosignature gases, then some nuances on exoplanet atmospheres, and I'll arc towards target planets. But because today I'm not going to be able to do the physics justice, I actually have a prize for the best question. This is very subjective, but it's my book, a book that I edited called Exoplanets. This book is from about 10 years ago. But it's not out of date with respect to the physics, which we did in this book. Every chapter has a different author to stand the test of time. So there you go. So to get started, let's just review the story from billions of years ago, when a simple single-celled life form, cyanobacteria, figured out something very clever: how to harness energy from the environment, how to use sunlight to get energy, and a waste byproduct gas that the cyanobacteria made was oxygen. Now, it took a long time, but eventually oxygen filled the atmosphere till today. It's about 20% by volume. So we humans, we need oxygen to breathe. But without plants and photosynthetic bacteria, we would have virtually no oxygen. So I always love to imagine that there are intelligent beings around on a planet orbiting a nearby star with the kind of telescopes we're trying to build. And when they look back here, they'll be suspicious there's life, not from city lights or the Great Wall of China, but from oxygen. It's sort of counterintuitive in a way, because we don't see these gases. But that's where we're at. So in my own research, I have this kind of guiding principle that I read in a National Academy's report some time ago. And it's this quote here: "Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it." Because the thing with oxygen is that although life has been making oxygen for 2 or 3 billion years, it hasn't always been at that 20% level. Now, 1 billion years may seem like a very long time to you, but considering our planet has been around for 4.5 or more billion years, there could be a long period of time when a planet that might have life doesn't show oxygen. So I spent a lot of time thinking about what gases should we look for? In an ideal world, from now and through the future, when our telescopes get better and better, what gases should we look for? And I made this sort of journey through chemical space, which is a space of all possible molecules. It's used in computers for drug discovery. People can generate literally trillions of molecules. There's vast numbers out there. And everyone takes a different slice through parameter space. So this is just my introduction, so it's somewhat of an overview. But when I was thinking about this, I just came across this idea I wanted to pursue, which I call in the end a crazy theory. So I was wondering how many of you get emails on crazy theories. I know you all do, so you can put your hand up. Yeah. Well, so my theory was, or my idea, not really a theory, was, perhaps all molecules are made by life. Everyone I could think of at the time, and I challenge you, not being chemists, to think about that. And this idea was bolstered by the point that, did you know that all gases in our atmosphere, not just oxygen, but all gases to the part per trillion level, with the exception of the noble gases, are actually made by life? That's not their dominant source, but they actually are made by life. Life makes so many gases. And to substantiate this theory, I recruited a couple of biochemistry colleagues, and I started with combinatorics of the big 6 biochemical elements: carbon, oxygen, nitrogen, sulfur, phosphorus, hydrogen. I put them all together. I got 6,000 molecules, but because atoms can be arranged in different ways, there's like 30,000, we scraped the literature and databases to figure out which were real molecules. So we took this idea, made a presentation, and I was gonna say, like, who does the MIT or Harvard professor go to? Like, if you have a crazy theory, you could go to your peers, but I go to the next level up. Nobel laureate, we went to talk to Jack Szostak, who I'm sure many of you know. So he took a look at this theory, or this idea, and you know what? He immediately found a counterexample of a molecule not made by life and crushed the theory. And then he pointed out I did my combinatorics wrong. I should have listened to my biochemistry colleagues. I'm sure you would have all done it the same way. But I took all these elements and put them all together in all possible ways they could bond. That's not how nature wants to do it. So that's why I put these molecules on the top here: ethane, ethine, or acetylene. So really, nature would take, you can have 2 carbons, but various numbers of hydrogens, depending on how many bonds you have. Anyway, it's just a little detail. So we went back to the drawing board. Here's an illustration. A sea of molecules fills chemical space. A subset of those molecules are sorted by our algorithms. We just want to be prepared to recognize biosignature gases of any kind. Now, in this work, it ends up being like a tangent that I'm trying to pursue separately. But there are this set of molecules, or fragments of molecules we call motifs, that are like never made by life, actually. And it has something to do with toxicity and the origin and evolution of life. And that's a story for another day. In the end, it turns out there are something like 16,000 molecules that are in gas phase at our Earth's room temperature and pressure. About a quarter of them are made by life. It's not really here nor there. But what is interesting is I'm showing you 3 streams in this illustration. The stream on the left are molecules never made by life. There's sulfur hexafluoride that's sticking out at you right there on your left. But in the other 2 streams represent 2 different kind of classes of biosignature gases. This is probably the most relevant part of my introduction. That is, one class, shown by this middle stream, are made up of molecules that are very common, like methane or hydrogen sulfide or nitrous oxide. And they're made by bacteria that exploit chemical energy gradients, potential chemical energy gradients. Think about like the ball at the top of the hill. Just push it a little and it will roll down, converting potential energy to kinetic energy. Well, what life does is it finds these chemical potential energy gradients in the environment, catalyzes them with an enzyme, and then the reaction proceeds to yield energy. So there's a lot of those, and these types of biosignature gases, they tend to be made in large quantities. But the problem is they also have many false positives, because the planet has the same molecules to work with that life does. So a good example is methanogenesis. Life at the bottom of the sea takes hydrogen, molecular hydrogen, and carbon dioxide mixed from above, and makes methane and water. But somewhere else on the planet, where the temperatures and pressures are slightly different, that happens anyway. So that's a problem, because methane, we want to search for life. We think about methane as a gas made by life, but it's also made, at least at our seafloor, on volcanic mid-ocean ridges. So what do we do with all this? We have a kind of process to evaluate classes of gases. What I told you about my database, it just here, all small molecule database, it's just the first step. Then we look for spectra, only a tiny amount of these gases, maybe 600 or so. They actually have measured or calculated spectra. This isn't your school here, SEAS, that's just what we happen to coincidentally call our computer code that generates model atmospheres. And we ask ourselves, does the gas of interest, is it unique? Does it stand out amongst other gases we expect to be there? Gases like, say, carbon dioxide or water. If it passes all those tests, that triage, we have to evaluate it through chemistry and photochemistry that I'll talk about a bit later. So I just wanted you to note, maybe overkill, but we're trying to find all possible potential biosignature gases just so we can be prepared for a future when we don't know what a planet would be doing. So for this introduction, A biosignature gas is a gas produced by life that can accumulate in an atmosphere to detectable levels. Oh yeah, sure. That's a good question. It's probably just a coincidence for this particular stream because there's only a few things here, but I'd have to take that away and think a bit more about it. Yep. And do feel free to ask questions during the talk. So we're just making this assumption that life elsewhere uses chemistry like Earth life does to extract and store and then use energy for metabolism. I don't know, maybe there's life out there that uses mechanical energy, like windmills, that doesn't need to store it, but somehow just uses it. In astronomy, we couldn't find that kind of life. So there are thousands of planets out there, and as I'm going to get to, we're on the verge of having the capability to find biosignature gases on exoplanets. So I'm not sure how much you know about this field. There's a lot of subtleties and nuances, and through my 3 lectures, I'm going to try to convey all of those, a number of those to you. So I'm going to move on to exoplanet atmospheres, and starting with this plot that is showing you just a subset of the exoplanets we know about. This is a log-log plot, and you can see here it's showing you planet size in Earth radii compared to semi-major axis in astronomical units. So Earth is a bit off here. Earth should be here at 1 and 1. And what you see is all these different points are planets. And there's several different techniques, 4 are shown here, that can find planets. Now, don't read too much into the clumps on this diagram, because to put all these planets on the same diagram, I had to convert. Some of the methods don't measure planet radius. So I had to do a sort of, people like to do kind of random draw on possibly likely mass radius relationships. But what I want you to know is that there's an incredible diversity of planets. You can see that there are some planets down here on the bottom left, some planets that are about Earth size, that are, wow, so close to the star, way closer than Mercury is to our sun. Because of Kepler's third law, these planets orbit in a very short period. They can have a year, the time to go around the star, less than a day, actually. They're these hot super-Earths. They're so hot, their surfaces are hot enough to melt rock. I could just spend the whole time talking about this, but I'll give you one more point here. There's this big clump. I said not to pay too attention to clumps, but do pay attention to this clump, where you can see there's a lot of planets here. The most common type of planet we know about so far within our biases is a planet 2 to 3 times the size of Earth, a planet that we have no solar system counterpart for. We're not 100% sure what they're made of or where they came from. So when I see this plot, I always like to think about when I was a student here at Harvard, a grad student back in the mid-1990s. I had actually finished a project on cosmology. It was like a master's level project, and it was time to find a PhD topic. And my then advisor, as we heard, Professor Dimitar Sasolov, he suggested I work on the brand new exoplanets. The planet 51 Peg B had been discovered just like a few months earlier. That planet got the Nobel Prize in Physics a couple years ago. And this was a very unusual thing because at the time, many people, including some on my own PhD thesis committee, weren't sure they were planets. We could only see them indirectly due to the effect on the host star. In this case, the planet and star, they orbit the common center of mass, and astronomers can measure the line of sight motion of the star. So at the time, I wasn't entirely committed to a career in science, but I love doing new things. So I felt the risk was worth taking. And I had to write a computer code to explain how the atmosphere of the planet so close to the star, because we found people found hot Jupiters very close to the star, how it interacted with the radiation and how the radiation heated the planet, and what the planet's atmosphere might look like. And so at the time, other people would tell me, you shouldn't work on this because they're not real. Why study their atmospheres? We'll never be able to see them. Well, today it's a big booming field. And one of the themes of my 3 talks is that the line in exoplanets between what is mainstream research is constantly shifting. So finding planets today, it's very mainstream, actually. But the other side of the line, or the line itself of what is crazy, that's actually my next 2 lectures. So here are atmospheres. I want you to see, this is like a large subset of the exoplanet atmospheres that are measured, these circles. So you can see that in the diagram, they're really extreme, right? They're the planets really far from the star, and there are these so-called transiting planets very close to the star. Now the circles are just planets that have been observed. We haven't necessarily discovered their atmosphere. I just wanted to remind you that Venus and Earth would look the same to our planet finding techniques unless we can see the atmosphere. They're about the same size, about the same mass, etc. So these yellow planets, they're all transiting planets. And these are planets that go in front of the star as seen from the telescope. You can see the fake planet on the top, and you can see here there's a drop in brightness. And when the planet finishes transiting, the star goes back to its original level. And that drop, that's related to the planet to star area ratio. So I want to make an assumption that you've all heard of transiting planets, but this is like the main way we find planets today. And I recently stepped down from a leadership role on this telescope. It's called TESS, and I'll talk a bit more about that in another lecture. But it's funny now because finding planets, we have a very standardized procedure, developed over the last couple of decades. And TESS is an MIT-led NASA mission, but here the Harvard-Smithsonian Center for Astrophysics plays a big role in follow-up. So the great thing about these transiting planets is we can study their atmospheres. And I'm going to walk you through this because this is a main takeaway from the talk, is how we study planet atmospheres, and later on where this is heading in the search for signs of life. So here you can see the transit on the bottom, and on the top right, that's like an artist's conception, a fake image of a planet transiting the star. And what do you see? The artist is highlighting the atmosphere, showing it as like a glowing ring. So some of the starlight passes through the planet atmosphere. Some light's blocked, others isn't. And what I want you to think about here, the concept that I'd like you to walk away with, by the way, I just put this equation of the intensity, the brightness, like it's an energy, is exponentially attenuated as it goes through the atmosphere. So here's what I want you to think about. Remember, the drop in brightness relates to the planet area compared to the star area. So think about the atmosphere at a wavelength where it's completely transparent. Then the area of the planet is that dark circle, right? That dark part of the planet. Now I want you to think about a wavelength where the atmosphere is opaque, completely blocks the starlight. Now how big is the planet going to appear? It's going to appear as big as the whole brown plus blue, this outer blue area, right? So you have to think about the transmission spectrum, we call it, as the planet looking a different size at a different wavelength. Because at wavelengths where the atmosphere is blocking light, the planet looks a tiny bit bigger. Okay, if you're with me on that, I'm going to move to some data. Here's an old favorite. It's a hot Jupiter transiting its star. And what you're seeing here is wavelength in microns on the bottom. The points are data from the Hubble Space Telescope. The lines are models. Just look at this right side of the diagram. You definitely see something, right? All you have to do is agree with me this is different from a straight line. Okay, so the planet's getting a tiny bit bigger. And if you look at the left side, you see transit depth. So there's a base amount the planet takes out. Okay, it's about 1.something%. And you can actually count this if you wanted to see how many, how small that signal is. So 1, 2, 3 parts per 10,000 it looks like. All right, so dozens of planets have been observed this way. Here's another one. This is one of my favorites. This is a hot Saturn exoplanet, and look, wavelength in microns. So here at 1 to 1.5 microns, you can see this very well-defined drop and rise, and this corresponds to water vapor. Question? These are just two different models with clouds, that have some scattering to them. So they're trying to fit this data on the left, which isn't very good, but they're trying to fit the data. So one model has clouds in it and one doesn't. And the clouds scatter light, in this case, clouds scatter light. So in this case, you're seeing another plot, and this features about 1 part per 1,000. So this atmosphere method, it's very well used now. There's probably almost 100 planets that have been observed or attempted to observe this way. And we try to figure out what's in the planet atmosphere, and that's how we hope to find biosignature gases. So I just wanted to walk you through a small exercise here, because it's really hard to do this, actually. And the signal strength, it relates to the annulus of the atmosphere compared to the area of the whole star. right? Because it's how much bigger that planet looks. And you all could work out this formula for annulus. It's just pi r squared of the outer to pi r squared of this inner circle. And so if you did that and cancel some small terms, you end up with this formula here. So the transit signal is 2 times the planet radius times this blue thing here, divided by r star squared. So it's just like, yeah, the area of the annulus compared to the area of the star. But the question is, what is this height of this blue part? It's related to something we call the pressure scale height. And here I'm just calling it 5 pressure scale heights. So if this was an undergrad class, perhaps there's some undergrads here, this was a good problem for you to work out. You have to take hydrostatic equilibrium. That's why our atmosphere doesn't collapse. Gravity is balanced by pressure, or the pressure gradient force. You could work that out, and combined with the ideal gas law and making a sweeping assumption that the atmosphere is isothermal, you end up with this equation on the left. The pressure drops off exponentially. And you might already know that for, I'm sure, I don't know if any of you have hiked Mount Everest. I haven't, but when people hike up there, they run out of air because our atmosphere is dropping off in pressure or density exponentially. And the E folding factor, just to make it convenient, Z is altitude. So the pressure at some altitude above some zero pressure arbitrarily chosen, it drops off as minus Z over H, and we call H the scale height. And the scale height, if you work through this math, you would get this equation. H is Boltzmann constants times temperature times the mean molecular mass over surface gravity. So we don't have time to work it out, so I worked it out for you, but I just wanted you to get a handle on the numbers for a second, okay? So for a hot Jupiter transiting a sun-like star, if we plugged all the numbers in, the scale height can be very big, 500 kilometers. We'll get a transit signal of about 1 part per thousand. And so the figures I showed you, one of them was 1 part per thousand. But these hot Jupiters, they're not going to have life. They're too hot. The atmospheres, there's no surface as we know it. It's just not going to happen. The outside temperature is 1,000, 2,000, or higher Kelvin. So for an Earth sun, it's a different story. And I put some numbers here too. You can work through this later because the talk's being recorded. And here I put some numbers in. The radius of Earth, it's actually 10 times lower than Jupiter, but this example I chose, a hot Jupiter, it's about 17 times smaller. The background star for a sun-like star is about the same. Scale height, our Earth's scale height is 8 kilometers. That's a lot smaller than that hot Jupiter, that's 500 kilometers. Because if you look back at the formula, Earth is much colder than a hot Jupiter. And our mean molecular mass for a hot Jupiter, it's hydrogen, which is small, that's 2 times something. And for our Earth, we have a mostly nitrogen atmosphere, which is a much heavier molecule than hydrogen. So if we were to work out all this math, we get our transit signal, that is the size of Earth's annulus compared to the area of Earth's annulus compared to the area of our sun. It's 1 part per million. So I don't know how many of you have to make a measurement at 1 part per million. Yay. Love to hear what that is after. But that's not going to happen for us right now for our telescopes that we're building. Our new telescope coming online, the James Webb Space Telescope, we just make an assumption it has a noise floor of 10 part per million. Could be worse, maybe better. So Earths are out of the question right now. Yes?
Is there anything that you can get from the dynamics of scattering twinkling?
Yes. You mean just from a different observation?
Yeah.
There is, and that's a later lecture. I'm just focusing, on transits today. We have other methods I'll be talking about in my 3rd lecture. So in this case, it's not going to work for us. We have to do way better than 1 part per million. And if you had time to work through these formula, what can we do here? For this transit signal, we could have a larger H. We could have a smaller R star. All right, I just put this note here for you, lecture 3. So what's really interesting is that if you look at this, we have to go to much smaller stars. And this entire field of transmission spectroscopy for small planets, it's all focused on small red dwarf stars. And I just gave you a tiny bit of math there to mull over. You can go through the notes later. But I just wanted you to see why that is. Didn't want to just state without any kind of argument for you. So we'll come back to that, but I wanted to talk a bit about atmospheres and give you a bit of why it ends up being such a complicated problem. It's something you don't usually learn about in physics, right? Like in undergrad or graduate physics, atmospheric science is usually in a different department. So I'm showing you a cartoon here, showing you from the surface there's gases emitted. I just called it bioflux, like life emitting gases with some rate. There's also volcanoes emitting gases as well. These gases will mix in the atmosphere. with the gases that are already there, and they'll be photochemically altered from ultraviolet radiation coming from the star. And so we have to kind of contend with all of that in order to understand what biosignature gases could accumulate in the atmosphere. So I just wanted to give you like a bit of an outline of, I wanted to actually touch upon the physics that makes this complicated, but I have to give you this sort of overview outline. You can think about this problem in an overview way, like solving 5 equations with 5 sets of unknowns. Always good to start with conservation of energy. In an atmosphere, no energy is created or destroyed. We have energy transport, which we use the radiative transfer equation and also convection. I already talked about hydrostatic equilibrium and the ideal gas law. And then we have photochemical equilibrium. We'd like to solve for the temperature, pressure, density for each layer of the atmosphere, as well as the chemical composition and the radiation. The radiation is a function of wavelength, and we can have lots of chemical species we care about. So there's some nonlinear physics in here, so we can't just take the matrix and invert it. We end up having to do something we call retrieval, which I'll get to in a minute. I actually had some slightly more complicated things here, and I'm debating how hard it would be for me to explain them. So I might just do it here without the equations. And I'll show you the equation. Don't get bogged down in it. I only have like 2 or 3 slides on this. We have this radiative transfer equation where just use the words, a change in intensity, which is our form of energy. It's just losses from the beam and gains to the beam. Just think of like a beam of traveling photons, okay? And eventually they're going to exit the atmosphere and record what is in the atmosphere according to the structure and chemical composition. The problem we have here is that we have scattering. And scattering, what that does is it essentially moves information giantly through the atmosphere. So instead of each layer being able to communicate with each other layer, a photon can scatter large distances and take the information from one spot to another. And this creates sort of a lot of problems when trying to solve this equation. Also, if you wanted to treat scattering properly, nothing in nature scatters isotropically. When light comes in, there's actually a probability distribution of which directions light will scatter into. If you want to take care of that properly, you end up having to integrate overall angle and use a so-called scattering phase function, which makes this an integral differential equation. We also have, in photochemistry, we need to think about every layer and what's happening with chemical reactions in every single layer. That would be all fine, but the question is, how are these layers connected? Because we have to think about the biosignature gases rising up through the atmosphere and accumulating in the atmosphere. And the thing is, we don't know. We actually sweep a lot of things under the rug here. We take all of our microphysics, which we don't know, turbulence and such, and stick it into a parameter we call eddy diffusion. And this works for our solar system planets because we can often measure trace gases and their distribution and then back out what this is. But it can vary over orders of magnitude. So at the end of the day, we are having some of these physical processes that make our equations complicated. And they also include a lot of unknown parameters. And finally, we have a lot we don't know about the planet. We know its mass and size, and we know radiation falling on it. We have some measurements of the atmosphere. But we don't know a lot of other things about it. Like, for example, that we leave that for Earth scientists, what's coming out of the planet. Okay, I'm not sure how clear all of that was, but I just want to say we have this set of equations that includes nonlinear terms, and we have a lot of things we don't know, like our boundary conditions are ill-defined. So what we do in this field, and this is one of the takeaways I want you to try to get, is we have so many free parameters we vary over, and we use a field that we've named we didn't name this was already called atmosphere retrieval. And when one of my students, his name is Niku Madhusen, he's actually a professor at the other Cambridge, University of Cambridge. When we started this, we simply called it the million model approach. Imagine generating millions, or as many as you can, trillions of models, and you ask which of those fit the data, right? And out of all the models that fit the data, you can constrain what your underlying physical and chemical values are. I'm sure some of you do this for your own field. So when we see water in the atmosphere, we might not know how much, but we can say, we can constrain the range of water, even if it's a big value. So we do this, but we can't just run millions or trillions of models. It's not going to work. We actually do a lot of parameterization. We don't solve for temperature even. We just sort of give it parameterized temperature pressure profiles. And we have to cleverly move through parameter space using priors and using like Monte Carlo or other techniques. And we call that atmosphere retrieval. I actually had a slide on it, but I think it's a little too complicated. So I'll just leave you with this summary. There's nonlinear physics, sort of a lack of input values because we don't know much about these planets, leads us to poorly defined boundary conditions, and that also exacerbates unquantified physical and chemical processes. So the takeaway I wanted you to have that in exoplanets, we live with our somewhat poor data and with a large uncertainty in what the planet is actually like. And we sort of come to a point where we're good with this as long as we can quantify the range of what's there. So we live with these unknowns by performing retrieval. We calculate these posterior probability distributions, which tells us about the underlying atmosphere values. So I'm going to come back to this a little bit later, but I just wanted to leave that thought with you. Like if you actually went and saw the code and tried to get like what it takes to do all this, you would think it's like complete overkill for the level of data that we have. But it's really something we need to do because we have such a range of uncertainties. Yes?
All the different uncertainties and associated universe problems that are retrieval, which is the worst?
Which is the worst? It also depends. So for this transit transmission technique, I would say it's probably which is worse. I don't know. I feel like the abundance distribution is poor. One of the problems is for transmission spectra, you have to think of rays from the sun going through the planet atmosphere. And in the end, they actually only be sensitive to a small part of the atmosphere. And so this isn't exactly what you asked, but one of the problems is we don't probe like enough of the atmosphere to constrain even the surface temperature. Actually, I'd pick that then. I would pick that being the worst one. Yep.
How do you model the scattering?
Like, in most cases, that's a good question, because I mentioned scattering as one of the problems. Yeah, so for this transmission spectroscopy, we usually just measure scattering as extinction, because a ray is going through the atmosphere and it scatters away. Sure, some might scatter back in, but most of it scatters away. So we really simplify that. Yep. If we want to think about the planet in reflected light, then scattering matters a lot more.
Can you repeat the questions?
Oh, sure. Yes, we just had a question of what's the biggest challenge, what's the worst variable to get back out of the inversion, the retrieval method. And I thought about it for a while and I said, I think it's temperature. With this transmission spectrum measurement, you end up only probing a very small part of the limb of the planet. And you don't have enough information to get the surface temperature, which is something you actually really care about when you want to think about a planet with the right surface temperature for life. The second question was, how do we treat scattering? And I just said, sorry, every question you ask, I'm going to say we oversimplify it. For scattering, when the rays are going through the planet atmosphere, we just treat it as extinction. Like it scatters the photons out of the beam. Yes?
Is it hopeless to look for fluorescence?
Is it hopeless to look for fluorescence? In the short term, I'd say yes, because it's really a very narrow wavelength, and it's not really a strong enough signal. But people have written papers about that. And in some extreme case, it might be a possibility. Okay, so I'm going to move on to target planets now and try to tie some of the pieces of these biosignature gases and atmospheres together for you. So I want to start out by saying that exoplanet atmospheres, there's a lot going on. We use the Hubble Space Telescope and others to study hot, giant exoplanet atmospheres. Exoplanets is big here at Harvard. There's people in a few different departments working on this. A lot of people out at Harvard Smithsonian Center for Astrophysics are working on atmospheres. So we have the Hubble, but we have something really exciting coming up. If you talk to like a large fraction of astronomers are waiting for December 18th at 7:20 a.m. Eastern. We have this new telescope called the James Webb Space Telescope. I just got this little movie for you. It's showing you the last time it was folded up in the clean room at Northrop Grumman Corporation in California. This telescope has to fit into a rocket fairing. The telescope is so big, everything has to be kind of squished together. If you want to Google this, there's like 4 separate videos. The next 3 which I'm not to the north part of South America, to French Guiana, to Kourou, where there's an Ariane rocket is waiting to receive it. So it's all ready to go. This telescope we've been waiting like 10 or 20 years for it. Actually, these giant telescopes, by the way, flagship NASA missions, they're typically 30 years from concept to launch. So here it is an animation of the James Webb Space Telescope in space, and here it is unfolding. This telescope, it's very big. It's 6.5 meters effective diameter, and it has to have a big sun shield, because you see the telescope is big. It doesn't have like a giant baffle covering it. So you can see here, it's deploying. It's going to take about a month to deploy, and it'll take a few more months to get to its destination, which will be the Earth-Sun Lagrange 2-point, far from Earth where it's cold and dark. But we still have to be able to block out our sun's light, and there's this special tennis court-sized heat shield. And actually, every layer is woven, it's a special material, every layer is woven in a different pattern, so the heat that comes in will be dispersed in different directions, so it doesn't like keep passing through. So we have like a lot of eggs in one basket. And this is sort of the telescope that everyone's excited to use for exoplanet atmospheres. So remember before, we were talking about the signal. And I said we've got to play around with these variables, so we have to have a really small star if we want to be able to observe small planets. And here's a real image of our sun, and there's a fake image of a very small star. It's called TRAPPIST-1. Any smaller and colder and it wouldn't be a star. It wouldn't be able to support fusion in its interior. TRAPPIST-1's about 10% of the size of our sun. You can see a fake Earth on here, Earth-sized planet, right? And look at that. Look how much, even just by eye, you can see it takes out way more area of the small star than it does of the larger star. Now, because the probability to transit drops off, it's related to the radius of the star compared to the semi-major axis, the probability is much higher to transit. The planet has to be closer to the star because of these small stars give off a very little amount of energy. And so everything ends up working in our favor. We can get more transits, the transit signal's larger. This is the way to go. So there's really this whole field of the search for signs of life on another world. It's focused on transmission spectroscopy of small planets transiting small stars. So just for a little mental break, let's go on a virtual trip to one of these planets transiting a small star. It might be, if we could go there, that the star would be very big in the sky, depending on the size of the star. Because again, it's like the campfire analogy. If the fire's really tiny, you have to stand very close to it to stay warm. This artist has taken the artist conception to show you in other planets in the system and to make the sky red. That we don't know for sure. But I like to imagine the surface of these planets being red. I don't know how many of you use a red flashlight. If you're an amateur astronomer, you'll have one of these. You know, everything is like red. I feel like that's how it would look on the surface. But one of the really interesting things about these planets is we have arguments that if the planet's on a circular orbit, that by tidal interactions with the host star over millions, tens of millions of years, which is a pretty short time actually, the planet will evolve into a low energy state where it rotates one time for every time it orbits, just like the moon shows the same face to Earth at all times. So actually one day would equal 1 year on this planet. But what that means if we could visit the planet, think about that for a second. The star, or the sun, would be in the same place in the sky at all times. So you could go where it's always daytime. Or if you're an astronomer, you might want to go where it's always night. You could go where the sun is always setting. Okay, this isn't like 100.0% true because there's some libration, so it would be moving around a bit. But yeah, that's what it would be like. So we can think about that being a sort of, fun thing. But it could be that visiting these stars could be a terrible idea because these red dwarf stars give off flares, which can be accompanied by a coronal mass ejection. And these stars have a lot of flares. So for example, you couldn't use your phone because high energy particles would knock out the electronics. It would be really bad for cancer, for your skin. If there's life on these planets, maybe it has to live on the far side, maybe the dark side, maybe it has to live subsurface or under oceans. We're not really sure. But these planets are what we have to observe. We're kind of doing what we can right now. I just wanted to change topics for 1 second here. That on our sun, like if you read the news, we were supposed to get northern lights like last night. We didn't get that. But our sun has flares. Our sun gives off, these balls of high energy particles that hit our magnetic field. But back in 1849 or so, we had a big event here on Earth called the Carrington event. Have any of you heard of the Carrington event? Okay, I want you to look it up, not now, but later, because it was absolutely phenomenal. At that time, there was an amateur astronomer named Carrington. He was from the UK, and he was looking at sunspots, and he saw some sunspots brighten. And a day and a half later, our Earth became electrified. At the time, people didn't really understand electricity and magnetism. Maxwell's equations hadn't been written down yet. But what happened was we had a coronal mass ejection, and it had embedded in it a magnetic field. And this came hurtling towards Earth, hit Earth, and it hit our magnetic field and induced a current. And at the time, just blanking what it's called, telegraph operators, they could take the batteries out and their telegraph still operated. Some of the wires caught fire. Supposedly, we could see the northern lights, like almost down to the equator, and here we'd be able to read a book outside at night by them. So why am I telling, no one died or anything, why am I telling you all this? Because first of all, we might get one of those events again, and that would be a disaster for our power grid. But I'm telling you this because this TRAPPIST-1 star, this really cold star, it gives off a lot of flares. And people monitored this star for 80 days. It happened to be monitored by a space telescope mission. And it had 40 flares in 80 days. And one of these flares, you have to do a lot of extrapolation because we're measuring it optical, and most of the energy comes out at much shorter wavelengths. Out of 40 flares, one was supposedly analogous to the Carrington event. With the TESS mission, we can see flares on stars, and we can sort of enumerate the giant flares. And some of these planets around, some of these red dwarf stars, they're giving off like an energetic event like that once a week or once a month. So not sure where that's going to take us, but this TRAPPIST-1 system, it's got 7 planets. They're all about Earth size. They're all about Earth mass. It's a very small star. Here's an illustration of the star compared to Jupiter and compared to our sun. Tiny star. I'm part of it. So each of these planets, by the way, is like prime for the James Webb to observe. And a few of these planets are in the star's so-called habitable zone, that as heated by the star with simple energy balance arguments, the planet's surface should be not too hot, not too cold, but just right for life. So I'm part of a team that has time already for TRAPPIST-1e, one of the planets. And here's a simulation. This is by one of my students. He did this before he moved to MIT to be one of my students. Okay, this is a lot going on here. So I'm going to just walk you through this briefly. This is a simulation of a transmission spectrum of TRAPPIST-1e with the James Webb Space Telescope. And this is transit depth. So you can, if you wanted to, count the number and see how small this signal is. And this is wavelength in microns. And he's showing you 2 different instruments. This one's just one instrument. Here's an infrared instrument. But I just want you to take a look at some of these peaks here. What you might be able to see, some carbon dioxide, methane, water vapor. He's also pointing out nitrous oxide and ozone, which are biosignature gas or related to biosignatures. What I want you to know, by the way, is for the James Webb Space Telescope and for observing these small planets transiting small stars, pretty much the thing people want to do is find out whether or not these planets have an atmosphere. Because of a lot of the energy coming from the star and the fact that these small red dwarf stars, they spend a very, early in their life, they're very hot, and it's not clear if these planets were able to withstand that. So there's a lot going on in this figure, but he's trying to figure out how many transits do you need to make a detection of anything interesting. And here are some posterior probability distributions. I wanted just to walk you through a few of these to sort of close the loop on this retrieval technique and what it buys you. So I want you to look at this. Okay, so I chose water vapor to tell you about. So at the bottom you can read this. This is like the log fractional abundance of water vapor. And you see here there's this probability distribution. So if you picked a random value from here, so this is basically trying to capture the possibilities of the underlying amount of water vapor in his simulated data. It's a pretty big spread, actually. And unfortunately, there's a tail that goes out to very small numbers. Yeah, so I just wanted you to get a bigger picture of what it tells us. So we could detect water, but we might not have a very precise value on how much water there is. If you look down here, you can see the width of this peak spans a few orders of magnitude. With carbon dioxide, it's a little better. There's definitely carbon dioxide found in this simulated data by this retrieval code. And so yeah, I just wanted you to kind of get a bigger picture. He is comparing 10 transits, data bin together, with 100 transits, data bin together. So you can take a look at the difference between this. And he's also comparing two different models, which aren't as relevant for us right now. So in my last few slides, I just wanted to go over our chance of finding signs of life on these other worlds. And by the way, if you look at his plots carefully, he has the biosignature gases N2O and ozone, a byproduct of oxygen, photochemical byproduct of oxygen. And he's showing you that with 100 transits, it's going to be tough. With 100 transits, you can probably detect it, but not very well. It's probably it would take a lot longer for me to explain this more clearly to you. But what we'd like to try to understand is, for the biosignature gases in question, how much biosignature gas do we need to be generated in order for it to accumulate in the atmosphere to detectable levels? So we do that. I'm going to skip my spectra because I want to be able to save time for Q&A. But we've done that in the form of this bar chart. And in orange, I'm showing you Earth values. So let's take methane, for example. Methane, it says here, methane is something like 500 teragrams per year of methane is produced by life. It doesn't all make it to the atmosphere because most of it reacts away. That's about 500 million metric tons. That's a lot. Life is producing a lot of gases. But we can run through our codes. We can ask ourselves how much of any gas that we are concerned about needs to be produced to accumulate in the atmosphere to detectable levels. It's a lot. For every gas, the blue bar is showing you that it's a lot. It's like equivalent to the amount of methane produced on our planet or more. Maybe that's not surprising because it takes a lot of, it's hard to detect atmospheres. It's hard for us to measure the amounts there. But what we found, the crux of it, is that this gas by life must be produced in enough amount so that it saturates all of its sinks. And specifically, if you know how much ultraviolet light is coming from the star, and how fast the biosignature gas is destroyed, I think maybe it's clear that life has to generate that same amount of that gas. Anyway, summary, we need a lot of gas, and we're just going to have to keep our fingers crossed that one of those planets transiting a small red dwarf star is going to be making a gas and making a lot of it so it accumulates to detectable levels. Well, I hope with all of that, you're ready to answer the question, what is our bullet point going to be? I mean, we have to get very lucky with the James Webb Space Telescope. We're going to have a handful of bright red dwarf stars nearby that we're going to be able to study for exoplanet atmospheres and for the search for water vapor or the signs of life. So to summarize, biosignature gases, life on Earth produces thousands of gases. Some have unique spectral features. All of them need to produce in very large quantities. Think equivalent to the amount of methane or oxygen produced on Earth or more. For atmospheres, transit emission spectra is a maturing science. Permanent ambiguities can be constrained, but we must live with large uncertainties in the underlying physical and chemical values. There are thousands of planets known, but we're relying on these very special, bright, small targets to be able to search for and study atmospheres of small worlds. We have a few of them. So our outlook is a generations-long search. It only starts with the James Webb Space Telescope. The story will continue with my lectures 2 and 3, but there's really way more out there in the future with new telescopes we're either building or hope to build so we can reach down to true Earth analogs. Thank you so much for your attention.
Yeah, I have a two-part question. I'll ask them one at a time. Do you consider the size or gravity of a planet to be limiting for life? That is, very large planets would not support life.
Yeah, there's a few things in there. Before I get to that, I just want to say that a large gravity is bad for us to detect because in the scale height, it makes the atmosphere, so it's kind of bad for us all around. I don't know.
Please remember.
I forgot to repeat the question. The question was, does high gravity make it bad for life? My first answer was to a slightly different question. High gravity is bad for the scale height and makes that atmosphere really smaller and harder for us to detect. I don't know about if it makes it bad for life. I personally don't necessarily see why. You know, people have done experiments for life, surviving, not replicating, but under very high pressures. So I don't personally think that that's a problem, but don't know for sure. As for large planets, that's something else, but large planets, we can show with a mass and size, we can get an average density, and we know large planets, they don't have a solid surface as we know it. And the question is, could you have life on a larger planet? Because those are easier to study. It would have to be life in the clouds, like literally life permanently aloft. Our own Earth, we've got some life in our clouds temporarily, but the large planets are somewhat disfavored because we can't get our heads around thinking about an aerial biosphere without a surface, but it might be.
Second question.
Can you use the mic?
Oh, yes.
So everyone can-
Second question is, you're looking for life as we know it, I think. What if someone looked from another star at our planet Jupiter, which is 90% hydrogen, 10% helium? Could there be little green men that breathe hydrogen or helium that represents life?
Yes, absolutely. Now, I like that question a lot. Okay, that's like so far, that's a really good question. So we ignore all of that being astronomers. We don't worry about that. That's why originally I made that ginormous list of gases, because we don't know what the underlying life is like. I'm just saying I'd like to be ready for any gas that's there in large quantities, very far out of chemical equilibrium. I don't care what gas it is, I won't know the underlying life, but surely it could be something. So life can survive in almost any atmosphere. Life here on Earth. To prove the point, I actually got one of my postdocs to do an experiment putting our Earth life, E. coli and separately yeast, into a pure hydrogen atmosphere, and the life was completely fine, it thrived. So that's not really a problem necessarily, but those aliens will have the same chemistry knowledge we have, hopefully, and they can work out photochemical equilibrium if they've measured all the reaction rates. So they could look at Jupiter, and they could ask themselves, is there a gas there so far out of equilibrium in the context with the rest of the atmosphere? So they could actually address that question, even though they wouldn't know if life is like ours or theirs or whatever.
Thank you.
Anyway, not for here. Is there a student that has their hand up? Is there a student? Take a student first.
Thank you for the nice lecture. I was going to ask a question about the source of the gases that you detect, and how much of it comes from like biotic sources and how much of it comes from like abiotic sources. Like let's say you detect like carbon dioxide on Earth, it can come from like biotic sources or it can come from like abiotic sources. Like I was going to ask like if you can do like some isotopic fractionation studies to like
Right,
kind of
okay,
answer that
yeah.
question.
Good question. So yes, in our search for biosignature gases, we're very limited because many of the gases, like carbon dioxide, they're already there geologically, and they're not good biosignature gases. Hopefully in the future, we might be able to do isotopes, but really we're struggling, as you saw, hopefully, that we can barely detect anything. So isotopes are out of the question right now for small rocky planets. Interestingly though, there's a sort of low signal isotope detection for a giant planet that's really far from a star using a different technique than what I described. So it is possible, but for life and fractionation, it's just, we've looked at this problem and it's just too tough right now.
I was wondering if you have any prospect in the far future if we will be able to detect chiral molecules in the atmospheres of exoplanets, and this could tell us something about homochirality.
You heard the question. Yeah, believe it or not, people have tried that for objects in our solar system. For one of Jupiter's icy moons, actually chiral molecules can generate circularly polarized light, actually. And people looked for this, didn't find it. It's something you could do, but the thing is right now, and maybe this is okay, let me think. I was just sort of trying to think, let me think for a second. Like right now, photons are our currency. We don't have enough of them. It's like being super, super poor. So all these great ideas, you might be able to do them someday, somehow, but we just don't have enough photons, you know? So sort of along that line between crazy and reality is the future where someone like you and your peers We'll have to develop giant telescopes way bigger than can fit in a rocket fairing. We'll have to have space-based assembly or manufacturing because we want to do those things, but we don't have enough collecting area right now.
Closely related, but maybe not so far as a chiral molecule. It seemed to be implied in your talk that going to even the slightly larger molecules was going to be very difficult. Is that true?
Well, the slightly larger molecules could possibly be difficult for a few different reasons. One is that it seems to be in nature, maybe with one or two exceptions. Like isoprene is a somewhat complicated molecule, has carbons and hydrogens, but a good number of them. It is generated in as high quantities as methane. So that's a case where a more complicated molecule is generated, but typically they're just not. Like if life is generating these more complicated molecules for hormones or signaling or stress, it's not the same as something wide scale exploiting a very common chemical potential energy gradient. So that's one reason. Secondly, as you get to a larger molecule, they end up having the same functional groups, the same stretching and bending as smaller molecules. Because large molecules are really just smaller molecules bonded together. So sometimes then you end up not having a unique spectral signature because it's already overlapping. And then thirdly, it's one of the things we're missing. I said we have like 16,000 possible molecules at room temperature and pressure. A lot of them just can be grouped into categories. But out of those, maybe 600 have opacities, have spectral line, cross-spectral molecular line lists where we can generate cross-sections and understand absorption. The more complicated the molecule, the longer it takes in people's computers to generate that spectra. So I'm not going to say never, but there's a lot going on for those molecules.
Can I ask a question?
Yes.
Maybe we're going to come back to what are the largest and what are the shortest transit times that people have access to? And I think the reason I ask is, I think I understood that much of what you said is associated with averages, and I'm curious to know if there is some dynamical information we can get from that.
Well, I'll answer the first question first, which was, what are the range of transit times? So the transit time, they can be like an hour for the small planets close to the star. And they're typically a few hours long, actually. But if the planet's really far from the star, because if Kepler's, they're much longer, but they're harder to find because they're more rare. So in terms of dynamic, do you want me to answer the dynamical information? Probably the only dynamical information you can get is, so the TRAPPIST system, the planets are actually too low mass for us to measure their masses. However, those planets induce a transit timing variation because they're gravitationally interacting with each other. So your transit should be strictly periodic, but it's not. It can be offset by like 10 or 20 minutes. And from all the offsets, you can constrain the masses of the other planets. Yeah, there's a few more complicated things, but that's probably the main one.
If not, let's thank
Oh,
the guest speaker.
more?
Thank you very much for the great lecture. And I wanted to ask about the graph you showed of the radii of the planets, exoplanets we have discovered versus their distance from the stars. And does that take into consideration the biases we have in our detection techniques, like the transit photometry favoring like short period planets and like radial velocity favoring like massive planets? And like, is there a way to adjust for that?
Good question. This plot does not take into account, let's call it completeness. These are all the planets we've found. It doesn't include what you're asking, which are what about all the stars we've searched whose planets we haven't found?
Repeat the question.
The question was, are the biases accounted for in this plot? Like, is this a true representation of the underlying planet population? And the answer is no. That's a lot of work. So in this case, it's just all the planets that it's a subset of the planets people have discovered. It's a much harder problem. That's like, say, the numerator, the denominator of how many stars did you search, where you should have found a planet but didn't. That is not included here. And there's some fields where people do all of that work. But right now, we're just too busy finding planets. It would be a good thing to do, though.
Any more questions? If not, let's thank Professor SEAGER for a wonderful beginning.